So we have a drag force or a viscous drag, the force which opposes the motion of an object through a fluid. And if you want to write the base unit, the drag force or a viscous drag, according to a Stokes, for a spherical object, it is given by a formula 6 pi eta r v. If I want the base unit of the viscosity, the eta, so what will the base unit? F is there. It will be 6 pi r v is equals to viscosity. What is the unit of the force? The unit of the force is Newton. But what is the base unit? Newton itself is what? It is kilogram meter second raised to power minus 2. Because kilogram, its mass into expression, or kilogram meter second raised to power minus 2. So we can write kilogram meter second raised to power minus 2. 6 is a constant, it's a number, no unit. Pi is again a constant, no unit. R is a radius, so what is the unit of radius? Meter. V is a speed, what is the unit of speed? Meters per second. So when we simplify this, this m can cancel with m, and this m can move in numerator. So it will be kilogram. If m move in numerator, this will become m raised to power minus 1. Second minus 2 is there. It will move up. It will be like, it will also cancel out. So this will become second minus 1. So the base unit of the viscosity is kilogram meter inverse second inverse. Is it clear? This one, the base unit. The viscosity changes with temperature. If we change the temperature, the viscosity does change. But for liquid, the change in viscosity is different from gas. Because for a liquid, if we increase the temperature, the viscosity will decrease. But for gases, if we increase the temperature, the viscosity will also increase. But how for a liquid it's different and for gases it's different? Look, in a gases, the particles are already moving randomly. Like these particles are not moving in a specific direction, they are moving randomly. So if I increase the temperature, so at a high temperature, the more random motion. So as a high temperature, greater random motion. So the flow, as we discussed in electric, the drift velocity, if you remember what happened if we increase the temperature of the conductor, then the drift velocity decreases. Why the drift velocity decrease? Because more random motion. So same thing happened here, that when we increase the temperature, more random motion. So as a result, greater random motion. So the net displacement decreases. If the net displacement decreases, so velocity also decrease. And if a velocity decrease, it means the viscosity, because viscosity is inversely related with velocity. If the viscosity, if it was flowing faster, it means it is less viscous. But if it is taking longer time, so it is more viscous. That's why when you see the temperature, different temperature, the viscosity of air is different. At 0, it was 1, 2, 3, 4, 5. So 1.5, 1.7 exponent minus 5 was there. But then it is 1.8 exponent minus 5 and then 2.2. So the viscosity has increased for the air. But for liquids, what will happen? Increasing a temperature decreases the viscosity. Why it's so? Because in liquids, the particles are already closer to each other and they have an intermolecular force. So when we increase the temperature, we reduce this intermolecular force. When we reduce this intermolecular force or we break this intermolecular force, so the particles start to move relatively at a higher speed. That's why when a liquid we increase the temperature, the viscosity will decrease. But for gases, it's opposite. Is it clear, the concept of viscosity and the temperature relation for gases and the liquids? So when we talk about the liquids and the gases, so the main reason, the relation between the temperature and the viscosity for a liquid, whereas for a gas, for a liquid, when we increase the temperature, the viscosity or tendency to flow will decrease, like to resist the flow will decrease. It will flow faster. What is the reason for that? Because in liquid, the particles are already close to each other. They are just moving past each other. But when we increase the temperature, they have the attraction between the particles. So when we increase the temperature, we are breaking these attractions. So we are breaking these attractions. So when we break this attraction, the particles will move faster. When the particles will move faster, what happened to the flow? The flow has increased. So if the flow has increased, means the viscosity has decreased. Or the velocity has increased, so means the viscosity has decreased. But in gases, what happened? The particle, when we increase the temperature, the gas become more viscous, means it resists the flow. When I say more viscous, it means it does not flow easily. What is the reason? In gases, the particles are already apart and they are moving randomly. So when you increase the temperature, the random motion increase for the particle. When the random motion increase, the net displacement will decrease. If the net displacement decrease, the velocity will also decrease, or we can say the viscosity has increased. Is it clear now? Next, we have a formula to derive a terminal velocity. For a terminal velocity means a constant velocity when the object is moving through a fluid. So if you want to derive a formula for the terminal velocity, so when an object is moving through a fluid, like let's say this is a container, and we drop an object through the fluid, the forces which are acting on the object, this object is going downward, the motion is downward. So the forces which are acting on the object, the weight of an object is acting downward, the upthrust is acting upward, and the viscous drag is also acting upward. What is the condition to reach a terminal velocity? When object reaches a terminal velocity, there should be no resultant force. The resultant force should be zero. So if the resultant force is zero, what I can say? I can say the upward force must be equal to downward force. So upthrust plus the viscous drag should be equals to weight, because upthrust and viscous drag are acting upward and the weight is acting downward. What is the upthrust? We already learned this formula that the upthrust is equivalent to what? It is equals to the volume of object, or you can say density of the fluid, density of the medium in which the object is moving, volume of object, and gravity. And it's on not only the volume of object, it's volume of a displaced liquid, but the volume of a displaced liquid, if an object is completely inside submerged, then it is also equals to volume of object. So the main formula of upthrust is it's a density of a fluid, volume of a displaced liquid, and into gravity. But when object is completely submerged, the volume of a displaced liquid is always equals to volume of object. So in place of this upthrust, we can say that it is equals to density of a fluid, volume of the displaced liquid, which is same as the volume of object because it is completely submerged, and gravity. What about the drag force? According to the Stokes, the drag force or a viscous drag is 6 pi eta RV. So we can say that the drag force is 6 pi eta RV. What about the weight? Weight of an object is mass times the gravity. So mass of an object into gravity. Now, the mass of an object, in terms of a density, density of an object is mass of an object into volume. Divide by volume, I mean. So if I need the mass of an object is a product of density in the volume of object. So density of a fluid, volume of object, gravity, plus 6 pi eta RV is equals to density of object, volume of object into gravity. Now, if I move this factor, the density other side, so what I'm left with 6 pi eta R 6 pi eta RV is equals to density of object, volume of object, gravity minus density of a fluid, volume of object, gravity. If I take volume of object, gravity common here, so it will be 6 pi eta RV. If I take volume and the gravity constant common here, so density of object minus density of fluid. What about the volume of object? Because when we apply the Stokes law, it is only valid for spherical object. So the volume of object is always 4 by 3 pi r cube. That's the volume of a sphere. Why we did not cancel these two? Because this is a density of object and this is a density of a fluid. So these two values are not same. That's why we cannot cancel. Now we further simplify. So this will be 6 pi eta RV is equals to density of object minus density of a fluid. What about the volume of object? Volume of object is 4 by 3 pi r cube times the gravity. Now we further simplify. Now it's a mathematical solution here. The pi will cancel with pi. One of the r cancel with cube, so they become r square. This will be 2, this will be 3 and this will be 2. Rest all looks same. So when I move this 3 in the denominator and viscosity also in denominator, so what I'm left with? I'm left with V with on the left hand side, which is equals to difference of the density of object and the fluid. This will be 2 here. This is r square gravity divided by this 3 also in division denominator and eta also in denominator. So 3 multiplied by 3 become 9 and eta. So this is a formula for an object which is moving through a fluid and reaches a terminal velocity. This is a formula which we will use to work out its terminal velocity. So we need the radius, the size, we need the viscosity so we can determine the terminal velocity. Or we can also use this formula to work out the viscosity. How we can use this formula to work out viscosity? Is it clear till this point, the derivation of the terminal velocity for object which is moving through a fluid? Any doubt in this? Okay. Now, how we can use it to determine, the same formula can be used to determine the viscosity. So if we say experiment to find the viscosity of the fluid, so the formula which we derive, that formula was the terminal velocity was a difference in the density of object and the density of the fluid, 2 r square g divided by 9 eta. If I need the viscosity, eta, if I need eta, this. So what will the formula? The formula will be viscosity. I just cross multiply with V. So the difference in the density of object, density of a fluid, 2 r square g divided by 9 V. So densities at a certain temperature is constant. So we can use a standard value for the density of any object which you are dropping. So these two we don't have to determine, like this will be constant. What we have to determine practically the radius and the speed. How we can determine the radius? So radius cannot be determined directly. What we'll do, we'll take a small sphere and we use a micrometer or we can use a vernier caliper and we place this between the jaws of a caliper. So we place this between the jaws of a caliper and determine its diameter. And from diameter, we'll get the radius. How to work out a terminal velocity? So how we determine the terminal velocity? We take a container and we fill it with a fluid. We place this object, which we determine the diameter. And on the container, we place 2 rubber bands. And the distance between the 2 rubber bands we measure by using a meter rule or a scale we measure. The moment we drop this sphere, as it fall, the moment it cross the first rubber band, we see that, so we start the timer. And when we see The moment it just reaches the first rubber band, we start the timer. And the moment it just reach the second rubber band, we'll stop the timer. So that is the time interval to travel between the these points, fiducial points. So using the stopwatch, we determine the time, and speed is distance divided by time. So the distance between the two rubber bands and the time interval. So we'll know its velocity, the speed. So we just have to substitute the viscosity is there, the density of object, like which material we use, so we'll know its density, which liquid we are using, we'll know its density. It's a constant value at a certain temperature. So 2r square g over 9 v. So radius we can determine by using a micrometer or a vernier caliper. Why can't we just take a full distance of a container? Reason is that because the moment we drop this sphere, it will not reach a terminal velocity. It will take some time to reach a terminal velocity. So we want to work out only the section where it reaches a terminal velocity. That's why the rubber band, the marking on the rubber band is not there at the top. The rubber markings are there at the bottom, near the bottom. So what is the reason? Because why I did not even measure the total length here. So the main reason is that because the moment we drop this, it won't reach a terminal velocity. It will take time to reach a terminal velocity. So we assume that in this region, this region, it will start to move at a constant velocity. That's why we use these markers, rubber bands. So we determine the speed and the radius is there. So using this formula, we work out the viscosity. The sources of error, we should avoid a parallax error in measurement of the diameter or the spacing between the rubber bands. We should avoid forcing the ball or pushing the ball into the fluid or splashing of the liquid. It should be gently released near the surface of the just near the surface of the fluid. We should gently release instead of releasing from certain height, because if you release from certain height, it will splash and it will have a turbulent flow which may not leads to a wrong result. So we should just release over the top of this container liquid level. And we consider that the object is not changing like the fluid flow around the object should remain turbulent, it's laminar instead of turbulent flow. Is it clear, this concept of the viscosity and how we can work out? Any question or a doubt?